All right, welcome everyone to the July edition of Friends of Lunar Volatiles. And this month, our featured presenter needs no introduction. It is Paul Lucey, who will be talking to us about some of the latest and greatest with the 6 micron emission band. So I'll just remind everyone to keep yourself on mute unless you intend to be unmuted. And Paul, in terms of questions, would you prefer if we hold things until the end, or are you comfortable with questions in between, or do you prefer questions in between?
No, if people want to jump in, that's fine, though I might say, oh, there's a few slides coming up. So
All
I'm
right,
not shutting
that
you down, just anyway. Okay.
sounds
Shall
good. All
I
right,
shall I get
take it away,
going?
Paul. Yep, whenever you're
Okay.
ready.
All right. So for those of you who may not have been paying attention, Casey Honeyball and I and a team that's shown here took observations of the moon using the stratospheric observatory for infrared astronomy, which allowed access to parts of the spectrum which are not accessible from the ground, in particular at 6 microns. So I'm going to go through some of the background and then dive into what the new data are showing us. So let's see, how do I advance? Okay, great. Oh, okay. So let's just start with some of the big picture issues. So UV and near infrared measurements that are related to hydration, they show time of day variations. So in the upper left, there's lamp, and you could see around noon, and there are better images of this, but around noon, the hydration related feature takes a big dive, and then it recovers in the afternoon. And the LAMP team has suggested this indicates release of water and also that the surface has a pretty high energy of desorption. So they inferred that. In the lower right, there's the initial data from Deep Impact, and I wanted to show this view because it pretty dramatically shows how the 3 micron band behaves on the moon. So on the left is a Clementine image showing the geometry. So we're almost looking directly down on the North Pole. The temperature image is in the middle, and it just shows the temperature goes up towards the subsolar point. And then the 3 micron band depth is basically just following temperature contours. There's no apparent afternoon, morning um, asymmetry, which is troubling for a number of reasons. So um, there's three models right now for trying to understand this behavior at least at 3 microns and possibly at UV. So one is ballistic migration, which started with Watson, Murray, and Brown, and many other studies that followed how a water molecule behaves jumping around on the surface. Most recently, Norbert Schorkhofer has had some papers on this. Ballistic migration requires water because hydroxyl is charged and doesn't easily migrate. There's a second model, which may be less well known, which is called inhibited diffusion. Now, in this case, deeply implanted hydrogen or implanted hydrogen from the solar wind migrates out of the lunar soil every day as it's implanted. But the model here is that as that hydrogen atom migrates, it'll occasionally link up with an oxygen to form a metal-stable hydroxyl that would cause the infrared absorption at 3 microns. This is in principle an Arrhenius process, so exponential temperature dependence. And so at high temperatures, the lifetime of these metastable bonds is so short that it's hard to see them, but at low temperatures, they linger longer, so you'll be able to observe that. This is requires the 3 micron band is due to hydroxyl. And finally, there's a potential that it's a photometric effect, that these observations are not due to abundance variations of any species. It's just a consequence of optical effects as a function of the viewing angle. Um, there is almost no photometric data in the UV. Abby Flom's working on photometry, has all of her data at 3 microns. It has some interesting results that I won't talk about today. And there's no data at the longer wavelengths that we'll be working with. Another issue is that both the UV and NIR can be due both to either water or hydroxyl. So right now, there's no validated algorithm to separate the two species. It doesn't mean it's hopeless. There's some pretty interesting systematics with wavelength that groups have looked at, like Roger Clark recently and Tom McCord about 10 years ago. And lunar mineralogy is relatively simple. So it could be the complications. For example, McLean et al. Showed that hydroxyl can mimic water in many cases, but the simplicity of lunar materials may allow separation, but that is going to require some lab validation, but not hopeless. But in lieu of that, water has a unique feature at 6 microns due to the HOH bend. It's a fundamental infrared absorption. Ludmila Starkina showed or presented this in 2006. Casey Honeyball and I weren't actually aware of this paper until after we took the data and Casey was doing her lit dive for her PhD. But Ludmila was the first one to actually put this in print, and then we tried to put it in action. So let me show a few examples of this feature in different cases. So these is a Morb glass that was stepwise heated by Shuai Li in his PhD thesis to do a calibration of the 3 micron band depth to abundance. And you can see there just past 6 microns, 6.1, there's a little divot there, and that's the famous HOH bend. The plot in the lower left plots the band depth of the feature, of the two features. And you can see how the 6 micron band depth goes essentially to 0 before the 3 micron band depth. And that's consistent with the phase equilibrium between water and hydroxyl in silicate glasses that Ed Stolper presented in 1982. In equilibrium, water will yield to hydroxyl at low abundances. And that's what we think we're seeing in Shuai's data. The 6 micron band has been mapped on Mars, a paper by Steve Rupp in 2004 with an obscure title that made it hard to find, something about zeolites. But at any rate, in the Mars spectrum, you can see a 6 micron peak, and then in the ASU also measured the 6 micron peak in dust in the lab. So we've seen this on other planets or another planet. These are some data from Spitzer that shows a lot of asteroids that have a little bump at 6 microns. I'm not sure this is necessarily water, but there's some spectral feature there that's fairly consistent. Maybe we're seeing an H2O emission on some asteroids. No one's ever published on this. This was just mining their data for examples. Dries de Keer, Carl Hibbets, and others wanted to show what a meteorite should look like in the wild as opposed to having landed on the ground and absorbing a lot of water. So they vacuum desiccated several meteorites, and here's just an example. In the orange curve, this is the meteorite sitting on the lab since it was collected. And it exhibits a fairly strong 6 micron adsorb water feature. But if you vacuum desiccate it, the feature gets much weaker, and they use the depth of the 6 micron band as an indicator that they had achieved what they thought we should see on asteroids. Kira Wilk recently published a paper on adsorbed water, and she did some nitrogen desiccation of Apollo samples and didn't see much action at 6 microns. You can see a little weak feature going on at 3. Um, um, but as I'll show you in the next slide, this feature on the moon is really weak, and um, it might not have been apparent in these data. So in the background here, these are actual SOFIA measured peaks. So you can see it makes a nice little Gaussian-like feature. Though the peak heights over this data set that I'm going to describe, the peak is between 1 and 2 microns, the mode of the distribution. And there are basically no features that are stronger than 4%. So this is a pretty weak feature. And just for context, if we use Schweiss calibration, and I'm going to circle back to that later, but if we use Schweiss calibration, the mode is about 150 ppm water in that surface, with a maximum around 300 ppm in these extreme cases. So this is what SOFIA data looks to the spectroscopists. The data set I'm going to show here is several flights that cover a wide range of the parameter space of things that people have proposed to control the 3 micron band depth. So is it Marian Highlands, maturity, all the photometric parameters, time of day. So we'll be showing you examples of all of these. The blue points are in Highlands, the red points are in the Mare. So we have a reasonable sample of those two terrains. You'll notice, just since we're inside baseball here, so some of these plots look like little squares of stripes, and some of them look like little dense rectangles. So we took data in 2 different ways. The dense, long, skinny rectangles are maps, and so there's some mapping papers out there, and you can actually see a nice picture of lunar craters and whatnot. The squares that look like they have stripes are supporting these regional studies of the behavior of water on the moon. So they aren't contiguous maps, but they cover a lot of territory. And most of the data you'll see today is derived from, not from maps, but from those regional studies. Okay, so we just take the whole data set as a pot, and we just, in a univariate sense, we look at every one of those controlling parameters, ignoring their potential for interactions just right out of the box. We see 2 strong parameters controlling the peak height. So we see latitude and temperature. So the caution, though, here is that the SOFIA data are very incompletely and very incompletely sampled. And so there's always a concern that there's false correlations between some of these parameters. So let me show you an example. So here's temperature versus latitude. And you can see this strange distribution of data points, and there's a big hole in the middle. This is an artifact of the fact that SOFIA's forecast spectrometer, which actually we use to collect the data, requires a cold reference. And so the telescope uses something that's called a chopping secondary. So it's a secondary mirror that alternates between looking at the sky and the target. Well, for the interior of the moon, that throw of that secondary isn't long enough to reach, say, the sub-Earth point. So for a substantial fraction of the data, but not a complete set of data, we use the unilluminated moon as a reference to try to fill in some of those areas near the subsolar point. At the very short integrations times we were using, there's negligible emission from that 100K nighttime surface. And we did several experiments comparing chopping against the sky and chopping against the night side, and and didn't see any systematic issues with the chopping against the night side of the moon. But the point here is that the data are very unevenly distributed. And so we have to be careful about spurious correlations. So here's an attempt to manage those potential correlations. So the plot on the left is the dependence of the peak height on temperature, where each of these lines is a narrow temperature bin of 10 degrees. And then the separation between each line is the increments are 5 degrees of temperature. So what you see at the lowest temperature, in this case, is 300K, and most of the middle temperatures, the latitude dependence persists in the face of um, of constraining the temperature to these narrow bins. At the higher temperatures, like 380 to 400, the correlation, it pretty much breaks down. So it's saying the temperature dependence is also influencing the latitudes when you're near the highest temperatures. Now on the right, this is the converse here. So this is the dependence um, of the peak height on temperature with dividing the data up into latitude. So if you look at the low southern latitudes and the high northern latitudes, you see that there's a inverse correlation of peak height and temperature. So the peak height is dependent on temperature, but at mid latitudes and there's almost no dependence in this very low values, 0.5% type of values, which is, these are offset, so you can't see the absolute values, but it's very low peak heights at mid latitudes, and then the high latitudes and low temperatures have peak heights that are more like 2 to 3%. So I'm fairly convinced we are seeing a latitude and temperature dependence of this peak. Though I should caution that there are other parameters that are correlated with latitude and temperature. So the emission angle in this particular data set is highly correlated with latitude. Just the peculiarity of the samples. It doesn't have to be, but it turns out in this data set. And temperature is computed from the incidence angle. So when I say this depends on temperature, you could equally say, well, maybe, Paul, maybe it's dependent on incidence angle. And similar here, maybe this dependence is on emission angle. I don't think so, but that's definitely an open question. I'll get back to that a bit more. So here's an attempt to separate the Mare versus highland behavior. So this is where we've constrained, on the left is temperature dependence constrained to latitude of 35 to 45 degrees, where we have a decent throw in temperature. And the red points are Mare and the blue points are highland. The black is the total data set. And in the response to temperature, it looks like a pretty decent difference in it's about equal to the error bar, but the highlands are seeing higher values of peak height, presumably water, and then the Maria are showing systematically lower values. In the latitude dependence, again, blue is highlands, red is Maria, less obvious difference. If that's all we had to go on, we might say it's insignificant difference, but the dependence on in the Mare Highlands in response to temperature, that's verging on compelling. Okay, so for the rest of the parameters, several other parameters, we constrain the data both in latitude and temperature. So a particular data set will end up being in a latitude band and constant temperature. So I'll show a few of those. So here's maturity computed from OMAT. This is temperature is constrained to 320 to 330, lat 40 to 50. And why these particular bands? So there's kind of three criteria. One is to preserve a large range in the actual values. A second is to maximize the number of data points so that we are seeing. And the third criterion escapes me. When I remember, we'll come back to it. But the point is we constrain those data so that we're not seeing the variation due to temperature, latitude, and maturity doesn't seem to have much relationship. Here's solar wind flux. So we compute the solar wind flux based on Schweili's recent paper on the magnetosphere. So we take the model flux distribution from Artemis, and then we assume the solar wind flux falls off with the cosine of the distance from the subsolar point. So the very low values are far from the subsolar point, low temperatures, except temperatures constrained here. And then the high values are closer to the center of disk or even in the magnetosheath. This is a little cryptic. It's tough to understand this, but that's okay. There's an overall inverse correlation of the peak height and the solar wind flux, but a nice trend in the middle. So not sure what's going on here. So I guess we just leave it as future work to understand this. Unfortunately, we can't separate fluence from latitude. In this data set, the solar wind fluence is highly correlated with latitude. So the fluence is we took the flux as a function of lunar phase, integrated that to get the overall fluence. And this was done by Lee et al. Also. So we can't say anything about fluence, but maybe the fluence is contributing to the latitude dependence. Here's lunar phase angle. So here's a photometric property we can measure without contaminating correlations. So each one of these data points is a different SOFIA flight across the moon. The phase angle is essentially constant. And then we constrained the latitude and temperature range. Oh, the other criterion was we wanted to have the latitude constrained at high enough latitude to actually see a throw in the peak height data. And this has a pretty strong dependence on lunar phase, so this may be a hint of photometric effects creeping into this data set. Okay, so here's time of day. So at a given latitude, time of day and temperature are correlated, but we didn't know what we would expect. And we see a relatively symmetric and approximately cosine dependent time of day dependence. And when we get down to implications, this is not consistent with current understanding of how a adsorbing species should behave with time of day. So we'll get to that. The latitude dependence, we think this has a very reasonable explanation. Let's just presume for the moment that it's latitude and not emission angle. So Jones et al., posited that OH is formed at low latitudes from solar wind, where the so it's implanted everywhere, but at at low latitudes, it's higher concentrations, the fluence. But this OH gets eroded by formation of water from adjacent hydroxyls that are activated by high temperatures. And when it desorbs to H2O, bounces around, transported to higher latitude, and then it desorbs to reform hydroxyl. And over, I think, centuries, this process will produce a latitude-dependent OH distribution. Then this OH pattern is impacted by the relatively isotropic micrometeorite flux. And Zhu et al. Showed that if you simulate micrometeorite impact into hydroxylated, actually a deuterated surface, you form deuterated water vapor. And then Honeyball et al., this may, I don't think these were directly connected, but the idea here is that some of that water that was formed in those micrometeorite impacts are actually trapped in the agglutinate glass. And so that produces a gradient in trapped water that mimics the hydroxyl distribution. That's the idea to explain, and what we're going to put out of paper that's under construction. The time of day and temperature dependence is problematic in a lot of ways. Um, so one is that based on Schwei's calibration, a very simple calculation. So you put a huge amount of water in the exosphere from early in the morning towards noon. And if you assume a 10 or 20 hour lifetime of water, and then distribute that water over a couple of scale heights to say 100 kilometers, a straightforward calculation just shows you're going to get something like 10 to the eighth water molecules per cc, whereas the LADI upper limit is around 1, and the Chase upper limit is about 10 to the third. So that's a problem. And then I mentioned Norbert's work and others on argon have shown that that if you accumulate water on the night side by some process, maybe micrometeorites or whatever, you will release that early in the morning, and you should see a peak in water abundance at the dawn terminator. But there's no supply to supply the water that appears after noon in the LAMP data, in the 3 micron data, and now in the SOFIA data. So that's a problem. Now the photometric effect, in order to invoke this, it requires that these 3 distinct spectral methods, very distinct spectral methods, all share a similar effect. This is amenable to testing in the lab. There's essentially no data in UV or 6 microns. There's literally no data at 6 microns. But this could be measured in the lab to see if there's an effect. And there is a very interesting effect at 3 microns. So I'll just, I won't spoil Abby's potential talk. The phase angle dependence hints at a photometric effect. And then the fact that we can't separate incidence angle and temperature, we can't separate emission angle and latitude, means that the door is open for a photometric explanation at 6 microns. Okay, so I'm just throwing out, and we talked about this last time, and Michael can chime in, but I had asked, could the water be migrating down into the regolith? And the issue there is if it's emitted from a grain surface, it has a reasonable something like 50% probability to get in the exosphere. So a factor of 2 doesn't help a factor of 6 problem. I mean, a factor of 10 to the 6. But there's surface diffusion, which is grains skittering around on the surface. And could there be an interaction between the thermal gradient that we have in the optical surface and the abundance of water as it moves during the time of day, assuming surface diffusion? Just a thought. Now, Kira Wilkes also suggested the calibration to abundance may be incorrect. And it is based on water dissolved in glass. It's not based on water adsorbed on a surface. So maybe we're drastically overestimating the time variable component. The latitude component, that's right in the middle of the Schwei calibration lane, but the adsorbed component is a different story. Maybe it behaves very differently in the adsorbed state. Okay, I think this is my last slide. So latitude dependence consistent with a Jones et al. With adding bits of Zhu et al. And Honeyball et al. the time of day and temperature dependent seems to be inconsistent with Laddie and Chase um, and Lace, um, and with models of how an adsorbed species should behave. You could do a 3 and 6 micron surface survey from a high altitude aircraft or Earth orbit at low resolution, which would produce much more uniform sample data than SOFIA. So like a CubeSat, or NASA has an high altitude aircraft that routinely works in the stratosphere and accommodates small telescopes. We are planning a 6 micron spectrometer that is being delivered to Intuitive Machines this summer for a launch in the spring. And that would collect 6 micron data from a high elliptical orbit, so relatively low resolution, ranging 500 meters to 4 kilometers. So sort of a little bit better than SOFIA. Um, so that may give us some very unique, interesting data. And then finally, laboratory photometric measurements in UV at 6 microns would be really great and may contribute to understanding what we're actually seeing. So that's it, Parvati.
Awesome. Thanks, Paul. All right. What questions do folks have? I guess I'll ask one just to get us started, but the upcoming IM ComSat 6 micron observations are super exciting. Like, so or are you able to say more about, like, would you get global coverage, repeat coverage?
Um, okay, the communication satellite has a mission, which is communications, and it has to balance. It has to see the Earth. The solar panels have to be a certain orientation. So we're gonna get targeted data. Um, we may get a few mapping orbits, uh, but we're trying to manage our expectations, and so um, we'll target the data to try to address some of these issues, and then neat individual sites that maybe we can use the Trailblazer target list. There's also another possibility that the periapsis of the orbit might be brought way down in the northern part of the moon late in the ComSat lifetime. And then we would be getting really high resolution data, sort of 30, 40 meter data. But we probably won't get global maps. The ConOps of trying to balance what we need to do, we need to look nadir, they need to look wherever they need to look, and they have to prioritize the communications mission.
Cool. All right, questions. So feel free to either raise a hand or put something in the chat, or feel free to go ahead and unmute.
Well, something I didn't get a chance to tell Paul yet in smaller meetings, this is Michael Poston, is that we've got some additional Apollo sample UV phase functions that we just submitted
Oh, great.
for publication. Just a couple more samples so far and more in the works. So hopefully we can solve that last point for the UV soon.
Yeah, that'd be terrific. And Michael, what did you think of surface diffusion as a process? Is that viable at all?
About the only way I can think of to make the surface diffusion hide, 10 to the 8 is if you're somehow able to diffuse, grain to grain without going into the gas phase
Yeah.
down deeper. But then I don't see how you reverse that when it starts cooling off in the afternoon.
Yeah.
There's a little bit of a thermal gradient that would partially reverse it, but the data all show a complete reversal, it seems.
Yeah. Um, yeah, I think this is at the point where hypothesizing is one thing, but a model is what needs to be run. And a Monte Carlo model could see if there's any there. Thanks, Michael.
Yeah, yeah. Like I don't. I'm not 100% sure how it fits together, but I know Menelaus Sarantos, who I don't think is online. Oh, Menelaus is online. But sorry to put you on the spot, Menelaus, but like, you've done modeling of diffusion of volatiles, across grains and between grains and into the subsurface. And I know you've focused on you've done some stuff on water, but also on other species. But is there something would modeling like that be able to explain this sort of observation of like a high near surface density at dawn and dusk that decreases in the middle of the day?
Yeah.
I guess all I can say, I haven't considered this. All I can say, the simulations I ran assumed it's coming from the gas phase and staking. But the fact of the matter is surface diffusion could be fast at these temperatures. And if you adopt the binding energy distributions or desorption, barriers that, Michael's work and Brown's work have suggested, you can definitely move material to the bound phases with lunar phases. So you could suppress desorption, but I guess with the binding energy distributions that we see, at least at the equator, you would still get desorption at some point of the day, I believe. That was the conclusion from the work I published in 2021. Yeah, maybe at the high latitudes, you can retain these materials, not in the gas phase, but yeah, we will need ever more availability, I think, of chemisorption sites to suppress desorption. I do agree, though, that considering inward diffusion should explain at least part of why the material becomes insensitive. I think that Jason McLean has run and Lucia have run a number of experiments that demonstrate that the OH actually moves further inwards. So at least part of the signal should be moving further into the grains.
Yeah, Tim's got his hand up, Parvati.
Yeah, Tim, go ahead.
Yeah, well, with respect to that question of material moving into the grains themselves, I mean, I'm still not clear. Are we looking at a thin film of water that would be sticking to the surface of all these grains, and something that basically you could see with your eye, or is this actually penetrating into the rims of the grains, and to what depth within the surface materials provides the signal that we're seeing in the 6 micron and 3 micron too?
Well, it can be, I don't know about seeing with your eye, but you can get very similar absorptions from water or hydroxyl in the volume and on the surface, as long as the net abundance when the light passes through it. So I think both are permissible. They don't exclude each other. So you could have a surface. Well, it's like the meteorite case where there's hydroxyl firmly bound in the mineral structure, and then there was some adsorbed stuff that they vacuum baked out, which
Then
was
what is the
contributing.
skin depth that produces the signal we're seeing?
Lunar materials at 6 microns are pretty transparent, so it's clear little marbles with water either inside or on the surface and we see several grains deep. I mean, it is thermal emission, so we're probably sampling that solid state greenhouse layer of hot material that's sitting a couple of grains below the surface. And then that has to pass through the cold layer on top. If the water is in that cold layer that's right on the top where grains can see, space and can radiate their power, if it's in there, I don't think we would see it because it's just too cold to emit Though I'm forgetting, Parvati, what was the temperature contrast that you were working with between the cold top layer and the interior? Was it
Yeah,
tens of
so
C?
this is in the epiregolith.
Yeah, yeah.
Yeah, so it's like it's so the modeling I've been doing with that is not entirely self-consistent because like so when I try and forward model it, I get temperature differences of like, tens of Kelvin, maybe,
Yeah.
30, 40. The lab measurements seem to show something much steeper, like closer to 100. Um, so
Yeah, the one paper I remember seeing, I think like 80C sticks in my head as the most extreme they predicted for that top few grain gradient.
yeah, and also the gradient is much steeper um, during the warmest times of the day, and so you get like so where you have like the bigger differences, the even though it's colder and near the top, it's still during the warmest time of the day. So it may or may not make a difference to how strongly the water sticks.
Well,
So
so we would
that,
be looking at sparsely distributed molecules in a layer maybe a few tens of micron thick.
or literally on the surface.
Okay,
And
or so an actual film on the surface.
well, it's
If we're talking,
monolayers, few
yeah, if we're talking
monolayers.
150 ppm, you're talking maybe a few layers thick, a few monolayers thick.
Yeah.
All right, let's do Jeff and then Kurt.
Hey, Paul, cool talk. Some of the correlations that you were showing, I was interested in, particularly the one with peak height and composition. Could it also be peak height and grain size if you assume highlands being exposed to more micrometeorite bombardment beating up, they might have a finer grain size, more surface area. Could that be going on? And related to that, were you able to disentangle the peak height solar wind flux so that you could see the two compared for highlands and mare? Or was that last correlation all types of compositions?
Yeah, I didn't constrain the solar wind flux with just Mare and Highland. That'd be interesting. These are the only two that I did. But let's see. Let me back up to your first question, which has already escaped me. About the grain size difference. Okay, I would say based on the Apollo 17 core, which is probably in place about 100 million years ago, and the uppermost part of the core is pretty highly space weathered, that the Mare Highland difference in that uppermost highly reworked zone is probably pretty small. I'd expect in that upper few tens of centimeters, it's just mature. But obviously could be wrong.
Any thought on what could be in composition space could be controlling the water absorption band? Or could it be temperature as far as Mare being black, highlands being
Yeah,
whitish?
but these are constrained for temperature. So
That's right.
but Michael did a bunch of work showing that water behaves differently on Mare and highland surfaces. The energy of desorption. So it's not unexpected. I don't know if I got the sign right, Michael, but at least that there's a difference.
I think I suspected that the sample I ran, the 12001, was probably not truly pristine due to some communications with one of the people at JSC after the paper was published. So I would actually look at, I think Brandt or one of the other people in Tom Orlando's group ran a different Mare sample after I graduated, and they found it less different. It was still a little lower, I think, than Highland, but it was a much smaller difference than the basically night and day difference I saw with the 12001.
Okay.
I know, Kurt, I know you had your hand up and then you might have lowered it, but
Yeah. Just going back to the diffusion idea is, would helium be a proxy perhaps, or some other species that we can measure more easily, like give us inroads into this question? Patrice Smith on the call has a qualifying exam coming up, and I've encouraged her to go think about this, but maybe it's a fool's errand. I don't know. Anyone have any advice on that?
Yeah, how's argon? Is that a proxy?
Might be better. For some mysterious reason, we don't see that with lamp though, so that's another question.
Okay.
I guess argon also has that like sharp, that sort of classic dawn peak and then decay. So maybe it's doing something different.
Well, and also argon is much more massive than water, so surely that has some effect. Ideally, it would be something like nitrogen, N or N2.
Yeah.
Brackets the mass of water at least.
Yeah, helium is going to be the closest, the next best thing to hydrogen if you're trying to look at that actual diffusion within the crystal structure of the grains, because helium's a few percent of the solar wind, and then it's much slower to diffuse, but it would still diffuse. I just worry. Yeah. I'd say with lamp, helium's probably our best shot other than hydrogen.
Just have tons of helium data is the good thing about that. So, okay. Patrice, we'll push on that. I'll see you on the call here. Great.
Yeah, thanks for asking. You definitely got a strong helium signal, so that'd be interesting to look into.
Yeah, the solar wind flux trend is interesting where like, there's a decrease and then maybe something different in the middle.
Yeah, I think more data. We do have more flights. They have less throw in the parameters, but this that could fill in some of this. This is pretty strange. Yeah.
And Paul, remind me, was this all one flight or was this over a few flights that line
This was
happened?
five. Oh, that line. I don't know if that's one flight or several. There's 5 flights in this data set.
Okay.
Yeah, and the model flux is based on Artemis, like a 10-year average, and it varies every month. So you have to take the flux with a grain of salt.
There are some assets that might have been observing the solar wind during these flights, though. It might be
That's probably true. Yeah.
worth a peek at those.
Yeah.
So
Yeah, in fact, I think Abby ran into one of the Artemis people, the space physics Artemis, and they said they're pretty sure that they could give us a flux for a lot of different times. So that's probably worth looking at.
nice. So Paul, general 6 micron spectroscopy question. Is there like a minimum temperature at which you get enough signal? I mean, for instance, like I guess like, if you're looking at PSRs, you probably wouldn't see much, but is there like a minimum illuminated temperature that you need to get a good signal?
It's very instrument dependent. So forecast was pretty sensitive. So we were able to see, right at the lowest temperatures that are still illuminated. It's kind of Luna incognita in terms of a lot of the systematics. We right now don't have a lab instrument that can measure in emission. We don't have the equivalent of a forecast. But we'd sure like to do that and start testing all of this. There's a little bit of data that was collected by the Germans, and they show some 6 micron emission features. They don't report on it, but you can see that in some of their data. And then this ASU spectrum, you can see this emission peak in the lab. Now, if you're using FTIR, things have got to be pretty hot to see. So when we're talking about trying to lower it down to the 250s, that gets that's going to take an integrating spectrometer.
Is the instrument on the IM spacecraft, like, is that similar to forecasts?
In terms of performance, we're waiting for it to come in. We're calibrating a very similar one right now, and it's supremely sensitive, so we would do great. But every one of these instruments has a personality, so we're not guaranteeing anything till we see it. And this is going to be the first time we work down at 6 microns with one of these instruments. So again, just managing our expectations.
Nice. What other questions do folks have? Menelaus, I see you have a question. Do you want to unmute, or I'm happy to read it out as well, but I'll let you unmute if you want.
Well, I was merely posing the question whether it is possible for the water once this 10 to the 8, I think, is not per cc, is not a density that is it, Paul, that this is an equivalent density for the flux that leaves the surface if you don't assume repeated bounces of that water?
Yeah, all I did just to get an order of magnitude was take the mass that's emitted over about 10 hours, assuming that's the lifetime of the water molecule, and taking that mass and putting it over 100 kilometers. So it's completely one-dimensional, just saying, okay, if we're gonna desorb that 150 ppm for 10 hours, this is the mass you get per square centimeter, and then distribute that over 100 kilometers. And that's where the 10 to the 8th came from. You can do this in several different ways, and you get similar numbers that are crazy high.
Yeah, I'm wondering whether the water itself only desorbs once, and upon return to the ground, it dissociates, and so it becomes more hydroxyl at high temperatures than water, and that prevents further desorption, and it moves it out of the 6 micron bucket. And I don't know if the relative importance of these features would be consistent with this hypothesis.
Yeah, I see. So if you, instead of using the lifetime of the molecule, use the hop time.
Yeah, the hop time is something like 10 seconds, right? The question is whether you eliminate it from the atmosphere after that bounce. So not 10 seconds,
so
10
that
minutes,
drops, but that drops it by an order of magnitude or 2. It's still a problem.
Well,
it helps.
I don't know. It's something to consider. If the ballistic lifetime is something like 10 minutes, and we're talking about 10 hours here,
so
that would be a lot of repeated bounces, perhaps.
Yeah, I mean, what we're trying to do is say, if we assume the calibration is right, we're introducing a lot of water in the exosphere, and how do we hide that from the mass spectrometers? And so, dissociative absorption really does help if you limit the lifetime to 10 minutes. But 10 minutes versus 10 hours, it's not even 2 orders of magnitude. So, but it helps. But this is a completely crazy, just simple one-dimensional model. A grown-up would have to do this work.
Yeah, I feel like I want to go plug it into an X-sphere model and see what I get. Yeah, cool.
I mean, you can use some of the existing models for argon that are published and kind of use them as a proxy for order of magnitude estimates.
Yeah.
I don't have those off the top of my head. Yeah, I think it'd be interesting if Milanos were able to put the desorption barrier really, really hard to overcome, but the surface diffusion barrier really easy, and just see if you get migration down out of the optical depth.
Or into that cold layer at the top.
Wouldn't that just increase the water signal?
It's too cold to emit.
But the
hey,
emission
Emil,
coming
thank
from
you
the warm
for,
layer goes through it.
proactively calling here.
Beth, I
Yeah,
think you
so
want to
I
mute yourself.
wanted to.
Yeah.
Oh, I think that might have been
It was
an
a hot
open mic.
mic, yeah. Okay.
Probably a unmuted both programs at once kind of situation. So what was I saying? Oh yeah.
But
So
anyway, a real model that, let's say you did what you said and just see at what depth and what temperature are the particles, and can you do a radiative transfer model on that, where are you absorbing water emission in that cold layer? Is it making it worse rather than better?
yeah, so if you have, that's what I was saying. If you have the warm layer, say 5 grains down, and it's giving us plenty of emission, but it's passing through a layer that's 100 degrees colder.
Yeah. So,
You know, if you used the water properties for that 100 degrees colder, what would you get?
yeah, you may absorb all that light.
Yeah, I guess it's also interesting to think about, like, so the Lattie observations, like, so the correlations of H2O with micrometeoroid streams that they found, like, so Mehdi Bena's hypothesis for that is that, like, so they were only seeing those spikes when the micrometeoroids penetrated below a certain depth, and so they have this hypothesis of like a desiccated uppermost regolith with water
Yeah, and it was
at
like
some
10
depth.
centimeters.
Right, yeah. So I wonder, like, what, like, yeah, I think that the diffusion question is really interesting, because, like, in a lot of the exosphere some models like Menelaus is considered diffusion in more detail, but I think, like, in some of the stuff that me and others, and some even, well, I guess Norbert has sort of looked at subsurface diffusion and exospheric transport separately, but in some of the exospheric models, we don't really look at subsurface diffusion in that much detail. So that seems like that might be something to think more about. Cool. All right. We are at the top of the hour. If anyone has one final question, we could do one final question, maybe. All right, Paul, if you want to have the last word, any parting thoughts?
No, just thanks everybody, and cross your fingers that spectrometer on that ComSat actually works.
Early 2026, you said?
Yeah, they'll probably launch something like March or April.
Cool. Awesome. All right. Thanks, Paul. And thanks everyone for tuning in, and we'll see each other later. Bye.